So we're talking about lesson 5 in this video. Lesson 5. And this conversation is about Diels-Alder, okay? Which I think you may have seen before, but we're going to treat this as if you have not. And we're going to do with this what you should do with every lesson, and I've sort of implied this up to this point, but let me just call your attention to it again. With Diels-Alder lesson 5, we're going to really focus on what's the main point. What are we looking for here, right? So we're going to start out with a summary. I don't know if that's backwards or not, but that's what we're going to do. Start out with a summary of the whole lesson, and then we're going to go to the mechanism. Look at that pretty carefully. And then from the mechanism, we're going to be able to say what the constraints are. Now, there's only one particular constraint that I want to talk about, but the mechanism really demands some things, and that's what we're going to mention that. And then we're going to talk about the stereochemistry of it, based upon the mechanism. And the stereochemistry, there's two implications: endo and exo products, and then asymmetric dienes and dienophiles, which I may not read to you. I may just let you do that on your own. And then finally, we're going to talk about the synthesis that we can do because we have Diels-Alder in our pocket. So, all right, let's talk about Diels-Alder. The summary is, this is it, and this is beautiful. The summary is, we're going to take a diene and a diene lover, a dienophile, and we're going to get from this a 6-membered ring, 6-membered alkene. That's the summary. So when I'm solving this, you're going to ask me questions in class, and I'm going to say, I don't know, I can't do that in my head. I'm going to go to the board and I'm going to write this out, this very step out. Okay? And then if in fact we've got something a little more complicated than that, then I'm going to first of all start here. That's carbon 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Then I'm going to number everything, and then I'm going to look at the more complicated structure and see what was different about carbon 1, and I'm going to make the changes on that and so on. And this carbon 1, those changes are going to still be here. If carbon 6 has got some changes on it, those are some differences. They're going to still be there, and so on. So this is the summary of the reaction. I think it would be prudent for you to etch this in your on your heart. Okay, so that's the summary. Let's talk about the mechanism. The mechanism of this goes like this. Pi electrons hit that carbon. These electrons hit that carbon. And these electrons hit that carbon. Alright? And if that's the case, I'd like you to prove to yourself that what we end up with is cycloalkene. If we're starting with these two, prove to yourself that that's where... And that's it. That's the whole mechanism of it right there. Okay? Now, the constraints. The one constraint that I want to deal with is, and only one, is that the diene has got to be in this configuration. If it's not, then we can't form a ring. This configuration is called S-cis. Okay, now in order to establish this a little bit, you tell me, what is the bond order of this bond? What's the bond order of that bond? I'm going to pause for a second. Please consider pausing the video and thinking about it. Predict what I'm going to say. Okay? The bond order of this bond is greater than 1. It is not a single bond. It is not a pure single bond. It does have some double bond character. Why, Dr. Kopik, how can that be? It looks so safe like that. Well, here's the reason why. Remember, we've got our butadiene, right? And this actually has a non-negligible resonance contributor that looks like that and like that. So you please, again, draw out that structure right there and prove to yourself that the bond order of this bond is not 1. It's greater than 1. So, what does that mean? That means that there's some resistance to rotation here. You can go from here to here, okay? But there is not free rotation about that bond because there's a bond order is greater than 1. So therefore we have a name for this: S-trans and S-cis. Alright, now in order for the Diels-Alder to occur, it has to be in the S-cis conformation. How could it not be in the S-cis conformation, Dr. Kopic? Good question. How about if we constrained it, say, with a ring? Do you agree that no matter what we do with this, it's got some single bonds in it, that's got some double bond character, yes, but it can flop around a little bit, but this cannot get into S-cis. Okay? So, we've talked about the summary, and that is this. This is the summary. We've talked about the mechanism. Here it is. And we've talked about one constraint. It has to be in the S-cis conformation. Now let's talk about the stereochemical ramifications. Endo-exo, actually, you know what I'm going to do? I really do want you to look at that on your own. Endo-exo, I think that Bruce just deals with it so much better in text than I can with a picture. You want to refer to page 378 for that. And I don't want to say anything else about that. Neither do I want to say anything about the asymmetric diene or dienophile. It's also on the same page. No, it's not. The stereochemistry. No, that's on page 376. So page 376, 377, 378. Those are interesting pages for you. You need to read those. Do bring questions to class, but I'm gonna let you chew on that on your own. But I do want to talk about synthesis. All right. So if we know, let's talk about the summary again. If we know that every Diels-Alder is going to look like this, every Diels-Alder is going to end up with a six-membered ring. They're not all going to look like that, right? We might have a ring. We might be looking at it from the side. Okay, this is the same thing. These two are the same. That's not alkyne, by the way. These are the same, right? Just looking at it from a different angle. So be careful. They're all going to look like a six-membered ring. If you get a multiple choice answer, and I have something like that, I or the ACS finals got something like that, just relax. Make it a six-membered ring. You know if it's Diels-Alder, it's going to be that. All right, so what do we have if we, in order to think in terms of synthesis, how do we get to here? What reactions can we get to there or to there, right? What things can we get to there, and what can we take from here? Let me give you an example. And this is always what you're going to be doing with synthesis. You're thinking, I know I've got this. This is my framework for my reaction. How do I get there? And here's my framework for my products. How do I get out of there? Okay? So for example, A. Suppose I take A and B, and I can make B into that, and I can make A into that. And I can make, and then I can take this. Come on in. Excuse me, folks. Come on in. I'll be with you in just a minute. And we can take this cycloalkene and turn it into, say, C. Then what you've got is a pretty elaborate synthetic pathway. I'm gonna finish this if you don't mind. I know I asked you to come back. Do you mind? Thank you. I'll be just a minute. All right, so let's give an example of how we can take. Let's start out with A as simply that. But let's say that we want to take that plus acetylene. Okay, and we want to make through several steps. We want to make cyclohexane, right? So in order to do that, we first of all would take that and turn it into that, right? And then we would take these two together and turn it into that, and then we would take those and go there. All right? So what I'm asking you is, what is reaction 1? What is reaction 2? And what is reaction 3? I'll give you a hint. All three of these are in the list of reactions which I'm sorry, I think that may have been off camera. We're going to take, suppose you were getting, I hope you saw that. I hope that wasn't entirely off camera. Suppose I gave you in a question stem, take these two and make cyclohexane. What would you do? Well, first of all, that's already in the summary, right? That's already in that form. It's not the confirmation, but just a little heat will make it into S cis, right? These two are the same thing. with some energy barrier between them. They're not the same conformation, but the same compound. So if we have enough heat in the system, we can interconvert between these two. So suppose I told you, take these two and make cyclohexane. What you would do is you would take this one and you would turn it into, you would take acetylene and you would convert it into ethene. And I'm asking you, how do you do that? I'll give you a hint. It's in the list of reactions which I told you that you need to know from Organic 1. Okay? Number 2, I would say, how do you get from these two things to this? That's reaction 2. I'll give you a hint. Look not far off. It is close at hand. Give me reaction number 2. And finally, what is reaction number 3? That's what I'm asking you. This is an example of a synthesis reaction. And synthesis are important for a couple reasons. Number 1, because you get a lot of points for them. Number 2, because they help us really appreciate the reactions and the mechanisms that we have on hand. Okay, I will post a video for the Diels-Alder mechanism. It's going to be pretty short, as you would imagine. It's going to look something like this. Right? The entire video is probably going to take just a couple minutes. And but I'll put that in your mechanism section. And for now, this is lesson 5.